Assalamualaikum warahmatullahi wabarakatuh. This is Statics chapter 6.4. We will be dealing with frames and machine. Right. So in the earlier part of chapter 6, we have covered trusses, and now we will cover the two remaining type of structure in this chapter, which is frames and machines. So first and foremost, I will just go through the definition. What is frames and what is machine, and how it is different from trusses, right? So frames and machines are two common types of structures that have at least one multi-force member. I repeat, frames and machine are two common types of structures that have at least one multi-force member, right? So recall that trusses have nothing but two force member, right? So in trusses, everything must be two force member, right? So if even one member in the whole structure is not two force member, i.e. multi-force member, is it 3 force member, 4 force member, etc., it will be frame, for example, no longer trusses, right? So that's basically the difference. And what is the difference between frame and machine then? Frame is basically frames are generally stationary and support external loads, while machines contain moving parts, right? So we will show you example of frames and machine, and as you can see from our own experience, you can determine that you can see that the machine is something that designed to have moving parts, right? Even though in our subject in statics they are not moving because it's still statics, right? Hopefully in dynamic it will be moving, right? But in static it's not moving yet, but the structure itself is designed to have moving parts, like what you see here, right? So but in terms of how to analyze, because it's statics, it not move, both frame and machine, the way we analyze is just the same, right? In terms of the step-by-step analysis. So that's why we covered it together, right? So only the level of difficulties might be different when you want to draw the free body diagram, etc., right? So steps for analyzing a frame or machine, right? So the first step is draw free body diagram, right? So it depends, right? Hopefully you have understand what we did in trusses, where in certain circumstances we might need to be able to solve the support action first before we can measure or calculate what is the force in each member, right? In some cases we do not need to solve for support action, we can straight away solve the members, right? In frames, sometimes similar situation can happen also. Anyway, so normally, so the first step is free body diagram. However, to draw the free body diagram, there might be some things that you should consider first, right? If you recall, in trusses, when you want to draw the free body diagram, the question you ask is there any zero force member, right? Just by looking at it, can you identify any zero force member? Because that will affect how you draw the free body diagram, right? In this case, in frames or machines, the question that you have to ask is there any two force member, right? Is there any two force member in the whole structure? Because for two force member, you know it's either intention or compression, right? The force must be along the line connecting the 2 points, right? So it will make a difference in terms of the free body diagram. So remember, the first question always ask, is there any two force member, right? Now, note that forces on contacting surface are equal and opposite, right? So for example, if a member and another member is connecting here by a pin, when you separate it, the force here and here, which is the connecting point, contacting surface basically, will be the same and opposite, right? But this equal and opposite, yeah. So if we have a pin, so normally we have x and y. So here you have x and y. So the x you draw here must be opposite to the x you draw here, right? So if this one you draw in this direction, here you have to draw in this direction, for example, right? And for a joint that with more than two member or external force, it is advisable to draw free body diagram of the pin, right? So normally in our exam, this rarely happen, right? But it can happen, right? For example, do we need an example? Okay, for an example, if you have Okay, let's say we have contacting point here, right? Just as I mentioned just now. So when you draw the free body diagram of these two members, right? So the forces, for example, if you assume it's spin, so it's x and y. So if you assume x and y in this direction, this will just be like that, equal and opposite, right? But if you have a third member, what will happen? If you have a third member, right? If you draw free body diagram of each member here, here, and here, then it will be confusing, right? Because previously we know that this x and this x must be equal and opposite, but now this x, this x, this x, how does it relate to each other, right? So it's best that you actually draw the free body diagram of the pin itself, so that everything is reacting to the pin. For example, in this case, if I have x and y here, that must be corresponding to the x and y here. And if I have, for this one, x and y here, that will corresponding to the x and y here. And another color, if I have x and y here, it will correspond to this x and y there, right? So everything reacting to the pin, so then you can have equal and opposite corresponding to the pin for each member, right? So that's the idea here, right? But normally we do not test you on this that often or ever, right? So far I have never seen this type of joint yet, right? In trusses obviously we have, because we draw the free body diagram of the point anyway, right? But in frame and machine I haven't seen any question like this yet, but in reality, in real life, it might happen. So that's basically the how you do it, right? So that's the first step, draw the free body diagram. The second step is develop a strategy to apply the equation of equilibrium to solve for the unknown. Look for ways to form single equation and single unknown, right? So if it's possible, right? So that comes with practice, right? It's hard to explain what that means, because when you have done a lot of practice, you will notice that, okay, if I go from this way, or if I select this equation first, etc., it will be easier for you, right? So that's basically the strategy that you need to be able to develop by the time you want to apply, in this case in exam, right? So there's a statement here in the slide, so I'll just go through the statement. I'll just read it. Maybe I'll write it here if I have energy to do that. Problems are going to be challenging since there are usually several unknowns. A lot of practice is needed to develop good strategies and ease of solving these problems. What does that mean? It means it will be challenging. Like, it's not going to be easy. So this is interesting statement to put in the slide. It is not me that put in the slide, it's the publisher of the book, right? So it's just to make sure that you do not have this dream or ambition, or is it ambition? You do not be in a situation where you expect the question to be easy. It will not be easy, right? It will be challenging. But if you have enough practices, inshallah you can do it, right? Alright, so straight away an example. So it's quite interesting because this chapter is not that long, even though there's a lot of type of structure that you maybe need to be able to solve, right? But the fundamental is simple, it's straightforward, right? So that's just manageable. We actually have covered the fundamental. We'll just go through the example, inshallah. So let's see. This is the example number 1. Okay, so I'll put the picture there, right? So the question says the frame support an external load and moment as shown. So you can see there, you have support reaction. You should have support reaction at C and A. There's a pin support there, and then you have the 400 Newton force, and then you have the 800 Newton meter counterclockwise moment there, right? So you need to find the horizontal and vertical component of the pin reaction at C and the magnitude of reaction at B. Alright. Do you understand what the question wants? Basically the question wants what is the unknown support reaction at C, and then what is the force at B. Alright, so take a look at the picture. Remember what's the first step? The first step is to draw free body diagram. Alright, free body diagram of what? Basically you have two members there, right? Member AB and member BC. Normally we'll separate them, right? So what's the question? Do you remember what the question that you should ask before you draw? Number one, is there any two force member? Right? Is there any two force member you can see? You should be able to tell by now, right? You can see that member AB is two force member. Alright, so that with that we can start to draw our free body diagram. Now, so basically, you will have two member like this, right? One member here and another member like that, right? So this is AB, this is BC, right? And then of course you have the forces. This is 400 Newton, and then you have counterclockwise of 800 Newton meter. Yeah, is it in the frame? Yes. Alright. And okay, another one, all the dimensions should be there. Should I? Okay, I'll put it. Because normally yeah, okay, I'll put it. To be fair, right? Because I do not want anyone to complain that why should I draw? Because in the lecture you don't even draw, right? So you have 1 meter here, 2 meters, right? Alright. Hopefully that's clear. Alright, so the question, so we have already identified that member AB is two force member, right? So this is two force member, right? So the question is, do you want to consider or assume it is to be under tension or under compression? Now, it is an assumption, but logically you should be able to think, right? From the structure, you should be able to see that it is pushing that. So in that case, A and B should be under compression, right? So in that case, if you assume it's under compression like this, F A B, F A B. So it means that this force is like that, F A B, right? And the angle is, okay, this 1 and then there's 3, right? So 1, 3, 9, 10. Square root of 10, is it? Is it correct? 1 is 1, 3 is 9 plus 10, right? 1, 3 square root of 10, right? So that's the angle there, right? What else? Okay, of course you have CX and CY, right? So that will be your free body diagram, right? So how many unknown you have? 1, 2, 3. Of course, this free body diagram is not going to be useful for any calculation because it's basically just FAB equal to FAB, right? So that's it. So in our calculation, so I'll just erase this one because the calculation mainly will have to use this one. Okay, any question? How can you answer, right? Alright, so with this free body diagram established, now the next question is how to solve, right? So if you haven't done enough exercise by now, you normally know what is the first equation that you should use, and normally for the most question, the summation of moment will be the first one, right? So in this case, summation of moment about point C equal to 0 is, I say, counterclockwise as positive. What am I writing? So summation of moment about point C equal to 0, counterclockwise is positive, right? So why we are taking moment about this point? Because then this 2 will be 0 and then we can solve FAB, right? So in that case, from that, so 400 Newton times the distance of 2, that will be positive because counterclockwise, then plus 800 Newton meter there, and then let's take the vertical one, so it will be minus, the vertical one is FAB 1 over square root of 10 then the distance of 3, and then minus FAB, then 3 over square root of 10, that's a horizontal, is a distance of 1, should be equal to 0, right? So from here you should be able to calculate what is FAB, right? And if I just look at the slide, they will give you FAB is 843.3 Newton, right? So verify that calculation. Alright, after you have done this, then the rest is straightforward, right? Summation of Fx equal to 0, then basically you have Cx minus 843.3 times 3 over the square root of 10 equal to 0, so Cx, you get your number there. And then for Cy, then you have summation of Fy equal to 0, then you have, in our case, in my case, I assume it to be downward, so minus Cy minus 400 plus 843.3 1 over square root of 10 equal to 0, then Cy, you have your answer, right? And if I check the answer in the slide, Cx should be 800 Newton to the right, 800 Newton to the right. So in our case it should be positive 800 because we assume to the right. And Cy, it should be 133 Newton upwards. So in our case, if you calculate, because I assume downwards, it will be minus 133 Newton, right? Meaning that it's 133 Newton upwards. So that's how it is solved, right? It's basically after you have established free body diagram, it's just equation of equilibrium, right? So that's the common theme throughout statics, right? Free body diagram, equation of equilibrium. Free body diagram, equation of equilibrium. So it shouldn't be that hard, right? It's free body diagram, equation of equilibrium, right? So the only issue is if you fail to get the correct free body diagram, or you don't know how to use equation of equilibrium. But hopefully you know, right? Because if anyone do not know how to apply equation of equilibrium, then why are you taking statics, right? Or why are you taking engineering, right? Okay, there's a lot of message coming in. Alright, so concept quiz. So any question? Why do I keep asking that? Any question? If you have, if you have any question, do write in the comments, right? Maybe you have question. I shouldn't. Yeah, maybe you have question. Just put in the comment, inshallah. Alright, so we will go into the concept quiz. Normally in this kind of lecture, I don't discuss concept quiz that much because it is more in the form of I can discuss straight away in the class. But this one is quite important, I think, right? So I put the picture here first, right? So the figure show a frame and its free body diagram. Hopefully the space is enough here. I don't know how to design this here. But anyway, you have the frame, and then you have the free body diagram, right? And the question is, if an additional couple moment is applied at C, how will you change your free body diagram of member BC at B? Do you understand the question? Meaning, because originally it's, okay, we just draw. Originally it's like that, right? Okay. So the question says, if an additional couple moment is applied at C, so if suddenly we apply here, couple moment there, additional, right? Additional than the original. How will you change the free body diagram of member BC at B? So member BC is drawn, the free body diagram is drawn something like this. Basically you have XY, okay, that direction is assumption anyway, and then we have like this, right? So how will you change this free body diagram here, right? Okay, can you see? how you will change the free body diagram at this point, right? So if you look at this question here, how will you change the free body diagram at point B there, right? So I'll just read the option in the slide if you don't have the slide. A, there's no change, still one force FAB at B. So still like the free body diagram, the FAB is just like that, still remain. Second, now we have BX and BY. So instead of the FAB originally there, it changed to BX and BY. Okay, that's second option. Third, you have BX, BY and moment B also. Fourth, FAB remain, but you add another moment. Between that option, which one is it? Please think. I will just, if you need to pause, you pause. Otherwise, I'll just go straight forward. Now, the answer should be, it will not change, right? So if you look at this point here, okay, I'll just go here. Right? If you look at this point here, right? The question is, why is this like this? Why is this force FAB like this? Is because this one is free body diagram. This one is two force member, right? So if it is on compression, then you have FAB like that. Now, when you add moment here, should you change here? No. Why? Because this one is because this is two force member. Now, when you change this moment here, this is this two force member change? No, it still remains two force member. So this force FAB will not change. It will be like that still. Hopefully you understand. Okay. Next question. The same diagram. So I'll erase this one. Right. Okay. The same diagram, but different question. Right. So I'll put again the question. So you have the frame and also the free body diagram, the original free body diagram. Right. Now, this frame will give you this free body diagram. The question says, the figure shows a frame and its free body diagram. If an additional force is applied at D, so that's why it circled D there. If you add a force there, whatever direction you add a force there, how will you change free body diagram of member BC at B? So it's exactly the same question. How will you change the free body diagram? Okay, so basically, okay, because the free body diagram is like that one, right? So how will you change the FAB? Is it no change, is still FAB? Or we have BXBY right now? Or you have BXBY and also moment at B? Or you just have FAB plus moment? Which one? If you need to pause, you pause. Otherwise, I'll just go straight in the answer, right? So it should become BX and BY, right? Hopefully you understand that. Why? Because originally this FAB is because this is two force member, right? When you have two force member, then you have something like this. But the question says when you have force here, right? So let's say it's like that. Is this still two force member? No, it's not. It's now three force member. Now this one is no longer like this. It will become X and Y. X and Y, for example. So this one should be corresponding to X and Y. So the answer should be BX and BY. Right. So make sure you understand the implication of whether something is two force member or not. When it's two force member, the implication is that the contacting point becomes corresponding to the two force member, regardless of what happened elsewhere. Right? Regardless. Alright. Okay, that's interesting. If I'm going to follow the slide, lecture slide, the slide is already over. However, I think I should give some extra examples to help you guys, right? So hopefully it helped, and if it did, hopefully you appreciate it, right? How you want to appreciate it. You can comment thank you down below. You can like the video, whatever just or you can, the better yet, if you can pray for me, inshallah, right? For risk, for health, etc., inshallah, right? So we'll go to, so basically what we'll do is I'll just put the picture over there and then we'll draw the free body diagram. That's what we'll be doing, right? So in this case, right, on whatever, where I put it there, how will you draw the free body diagram? Now, the best is you pause, you try, and then you continue and see how it matches with my answer or what I draw here, right? Because that's the best way how you want to learn, right? You try your best answer and see where you make a mistake, and then you know how you want to improve. Because if you just do not try and just blindly follow, normally a student will think, okay, I understand, but you have never tried to test your brain whether you actually get the same answer before that, right? And the benefit that you get will be less, right? So do try, pause, do try, and then see, right? I will not give the time to try in the video, because otherwise it will be too long. So it's for you to pause and continue, etc. Up to you, right? So there are two ways, or several ways actually, to draw the free body diagram, and all are correct, but sometimes some free body diagram is not that beneficial in terms of getting what you want, right? So one way, because from that one, right, one way is you just take away the support reaction in terms of not take away the support at A at cable D, for example, right? So that it become a free body diagram of the member as a whole, right? Not the member, the body as a whole, right? So basically, if you do that, what you'll have is something like this, right? So this one, and then this one, right? So basically, if you take all of this to be your body, because remember, free body diagram, you have to specify what is your body, right? So now this one went like this. So you have here force, which is 500 Newton, and this is, let's say, FD, and then for example you have AX and AY. Okay, can you see here? I'm out of space here. I cannot go there because I will disturb that picture, but so I will go out of the frame for some second. So this is one possibility of a free body diagram, right? So basically, this is the force, and then you take away the support here, and you take away the support here. That's one way to do it, right? Can you solve this one? You should be able to solve, because you have 1, 2, 3 unknowns, right? So you have 3 unknown, 3 equation. What is the 3 equation? Moment, force Fx, Fy, right? You can solve. But if you want to take out everything, for example, right? So even the pulley you want to take out, right? So meaning that, for example, it will be something like this. Okay, the aspect ratio is not the same. Right? And here and here, for example, right? Hopefully you can see, right? Meaning that you take out also the pulley from the member, right? So become, this is the pulley connected to this point, this pulley connected to this point. Now, so for the cable, right? For the cable here you have 500, so this should be 500, and this cable goes to this point, 500, right? Hopefully you can see. Now this cable FD here, let's still call it FD. So this is FD, this meaning this is FD, this meaning this is FD, right? Now, and then X and Y is still the same. Okay, let me check. Is it still in the frame? Yes, it is. Alright. What is happening here is that this is actually a pin at this point. So let's say, what is the label? C. For example, I select this to be CX, CY, an example. So you'll have something like this, cx, cy, corresponding one, right? So here it's point B. So if I assume here bx, by, this will be bx, by, right? So as you can see, if you detach the pulley from the member like this, the number of unknown will be much more, right? And it depends. If the question actually asks, what is support action at A, what is the force at cable at D, then this will be sufficient, right? This will be sufficient. But if the question, for whatever reason, the question actually asks, what is the reaction between the pulley and point B there, right? So you actually need this one, bx, by, right? So it depends on the question, but rarely the question asks for bx, by. So there's no need to detach. So that's why normally we keep the pulley with the member like that. Alright? Hopefully you understand that. Alright, so next. Nice. This one. Okay. Pause, draw the free body diagram, and then continue. Right. Of course, if you do not want to try and you just want to continue and you want to repeat next time, okay, no. If you, but it's advisable that you try, and then if you cannot go anymore, then you see the solution and okay, the effect is more. Anyway, so here, what do you have? Okay, regardless of the question, right? We just focus on free body diagram, right? So the first question you have to ask again is there any two force member? Is there any two force member? You should be able to see AB is two force member, BC is two force member, BE is two force member as well, right? So in that case, if you draw the whole, what do you call that, arm or something like this, which is connected to the whatever this thing, and then basically you have two force member here, two force member here, and then two force member like this, right? Something like that, right? Okay, my drawing is, this is like a map of different island in Indonesia maybe. Okay, so two force member, right? So if you assume, like for example, this is under compression, which is this is FBC and FBC, right? Hopefully you can see this one. Hopefully you can see this in a full screen and still the resolution is okay. Alright, so if this is two force member, right? So first, if this is assumption to be in compression, so at point C here, it will be something like this. Correspondingly is FBC here, right? And for this one, if this is also under compression, which is FAB, then at this point here you have FAB, right? Of course, this question is just for free body diagram exercise, right? Because in real free body diagram you have to indicate what is the angle theta, but in this question you can see that there's no theta given, so this is just to have an exercise to see whether this intimidating diagram is actually difficult or it's actually easy, right? So this one, let's say it is under tension, right? Let's say, just to make it interesting, so FBE, so correspondingly here FBE, right? And then at here you have point F, you have Fx, Fy, for example. All these directional assumption, and then point H. It depends. Okay, wait. Okay, HI is also two force member there, so it's just also FHI, for example, right? So this two force member here is really not compulsory most of the time, because normally it's not beneficial in exam, or not beneficial in exam, not beneficial for calculation, because in calculation there's no calculation here, is take away FAB equal to FAB, etc. But it's sometimes helpful for you to be able to visualize, right? So I put it there. Unless in the exam the question actually asks draw free body diagram of that member and that member happen to be 2 force member, you have to draw because the question asks so. So okay, so we have one thing missing is point D here, right? This is pin, so you have dx dy for example, so correspondingly, for example like that, right? So hopefully you can see it's quite small. So it's not that difficult actually, right? It's not that difficult, right? Of course, if you see this theory, what is going on? There's too many islands there. But if you just separate the members, you draw the member and then you go one by one. Okay, 2 force member, you settle first, and then what is the corresponding force, and then pin xy 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 xy. So it's not that difficult, right? So hopefully by now you think, oh, this is actually easy, right? What else? Alright, this one, pulley. Okay, can you draw free body diagram? So normally in the class I will show something like this and you will see that it's actually quite easy, right? Okay, so what to do? So we have 3 pulleys that we can consider. We have pulley there, and then we have the pulley here, and then we have the big pulley up there. Is it in the frame? Yeah. Okay, so here you have 600 Newton. Can you see that? Alright. And then you have 3 forces, right? Is it the same force? Is it the same force? It should be the same force, right? Because it's the same cable that goes around and around and around there, right? So let's say this is P, 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 right? So that's the free body diagram. And to solve this one is actually straightforward also, right? Summation of Fy equal to 0, and then you get P equal to 200, for example, right? Now, so next free body diagram is this one, and then that one, right? And this one, what is it? It's actually the same P, right? Because it's the same cable going around. And then this one you can label it as, I don't know, let's use another one, T, that's common, right? So let's use T there. And then that T is actually connected to here, right? Correct? And then you have another cable here, which is, I don't know, just use something else there. And what about here? This one is which cable? It's either cable this one, right? From down here, so it's P and P, right? And of course by now P is already solved, T is already solved, right? And you can solve for R if the question is like that, right? So as you can see, the free body diagram is not difficult. Okay, now this is the next question. Can you draw a free body diagram here? And you should be able to draw this one, right? Why? Because this is actually in the lecture just now, right? If you cannot draw like this, draw this one, I don't know. If you are watching this at home, call your mother, ask her to come and smack you in the head or something, because you have to pay attention, because this one is just in this video, right? So basically the first question is what? Is there any 2 force member, right? And you can see that member AB is 2 force member, and then you just draw accordingly, right? So basically, because this is a 2 force member, let's say it's under compression, so meaning that this one will be corresponding to that one, so this one, and then you have X and Y there, straightforward like that. And again, I do not draw the dimension just because normally we discuss about the forces, right? Because the dimension, I think you know what to do, which is that you know the dimension. So I do not focus on that, I just focus on the support reaction, etc. Just because that's mainly where the student get the confusion from, right? But when you draw in the exam, please draw all with the dimension, the angles, etc. because that is part of the marks, because that is part of the free body diagram. Alright, next. Alright, looking at this guy there. I'm not sure what is this guy doing, but I guess he's pulling the cable, right? Because he cannot be pushing the cable. He's pulling the cable for sure, right? So draw a free body diagram. Alright, so what element do we have here? So, the first one is the beam on the bottom there, right? So you consider just the beam there, right? And then there's the guy standing on this one. So I'm not sure why is it. What is this? Okay. Suddenly become a mouse or something. Where's the head? I don't know why, how to. Okay, right, whatever. So there's the guy there, right? And then there's the pulley, right, on this side. Correct? And of course, on the upper side where the cable goes around, that's not important, right? So because if you can see, because now the position that I draw here, this one, because I don't have enough space there, unfortunately, right? But it's you should understand, this is pulley E there, right? But what I'm saying that all the cable that go from F to here, and then going up to D, and then go to C, and then go down, that's the same cable, right? So now, if you label it, if I want to label this T and T, right, where does it go? It goes to just about on this one, right? So this one is also T, right? Of course, tension, right? And then on bottom here you have normal direction B, because there's a roller there. Is it? It's roller there, right? And on the other side here at A, here you have AX and AY, right? It's a pin. And here, okay, here should be the same here, right? So if this is P, this should be P correspondingly, right? Why is it upwards? Because it should be corresponding, right? From the perspective of the person, the cable is actually pulling it up, right? But from the perspective of the pulley, the guy is actually pulling down, right? And then the direction between the leg and the platform, right? So from the beam perspective, the man is pushing it down with the weight, but from the man, this beam is pushing it up so that he is staying in place and not fall down, right? So that's basically the free body diagram, right? It's not difficult, right? So if you just saw the problem there and you think, oh my goodness, what is going on, this is just so difficult, it's not difficult, right? So if you just draw the basic component, you have the beam, and then you have the person, and then you have the pulley, and then just draw one by one, and then you can solve, right? How many unknown do you have here? One. Okay, it depends, because we do not know what is the value that is given, what is not, right? But normally it is, okay, this one there's nothing here, right? Unless we have the weight of the man. Yeah. Okay, if you assume, because it's normally the man will not be weightless, right? So if you assume that the weight, then you have the weight there, right? But because this is just drawing the free body diagram, I don't have the actual question, so we'll just draw, right? And we just solve accordingly. Alright, next. Okay, can you draw the free body diagram? Okay, you have enough time, right? Alright, so the first question is what? Is there any two force member, right? And yes, there is, which is member BC, correct? So member BC is two force member. So this member is to force member. Do you want to assume it is under tension or compression? It can be either way, right? So if you want to assume under compression, it will be something like this. Right? Why? Because it must be along this line. Correct? So let's say FBC. And then so at point A, you have the x and y component, of course, A, x, and y. And then here, correspondingly, you have this force F, B, C. And then at the cable, you have 400 Newton, 400 Newton. Not difficult, right? Not difficult, right? So it's quite straightforward so far, right? Okay. Now, to the next question. You can try, pause the video. After that, we'll continue. So, basically, the only thing that you have to deal with here is the pin at A, right? Normally, you assume that as a pin, right? In terms of the effect, right? So basically, you have, if you disconnect the two, it will be something like this, and then something like this, right? Where the connecting point E is somewhere there. Okay, my drawing is way weird, but and then you have the whatever things that is being hit there at point B, right? So that is this one, right? So if B is being clamped, right? Normally it is being clamped, so B is being compressed like this, right? And then the corresponding one will be here, which will be this one, and here will be this one, right? This one is corresponding to this one is corresponding to this one, right? And at point B here, and at point A here, is basically x and y, right? And then you have the force, where is it? Sorry, I'm confused which is which. Okay, force here and force there, right? Hopefully you can see. So basically the only thing that you have to deal with there is to understand, okay, that at B it is being clamped there, so from the perspective of the ring there, it's being clamped, but from the perspective of the clamping thing is the opposite way, and then at A is just xy, right? So it's not difficult, this one. What about this one? Pause and then continue, right? Alright, so basically you have the two member, one member here, and then another member like this, right? Okay, the easy one first. Okay, some of the things are given from the beginning. So there's a force here that is given, and then there's a moment here that is given, right? And then the easy part, right? At A you have AX, AY, for example, right? And then B you have normal B, right? And okay, point CD, member CD, is it two force member? It's not, right? Because there's a force there, etc. So at point D you have dx and dy, for example, right? Now the only question left is point C. What is happening at point C? Right? Can you imagine the reaction? The reaction should be normal, right? Because it's basically a slot like that, something like that, right? Yeah, it's my angle, right? And then you have the pin there, right? So basically, this one is free to slide along in the what do you call that, in the space there. But it cannot move in the perpendicular direction, right? So you have to assume either because you cannot draw both way, because at any particular time, if this one tend to go down here, it will be restricted so that it is in that way. If this one want to go up here, it will be restricted from this direction, right? So it just basically should be perpendicular to this line. So if you assume like this, then it will be like this. If you assume the opposite, it will be the opposite, right? Normal at C. Right, so it's nothing is difficult so far, right? If you understand, straightforward. Again, should I even show you this one, because this one is straightforward. Alright, if you want to try, pause and then we'll continue. Right. Alright, so basically you have this thing here. There's one up there. Right, so basically, okay, the aspect ratio is going off. So basically, you have P here, which means P here, P here, P here, and P here, right? Because it's the same cable going all the way around, right? And then if you have, let's say this is T, so meaning that this is T, 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 and then this is 800 Newton, right? So again, there's nothing difficult there, right? Of course, you have to take care of all the distance here, right? So make sure you try that one, right? So I'm just focusing on the force right now, so it's straightforward like that. Right. When you have drawn it, it seems simple, right? So make sure you try everything, then when you see it again, it's, this is so simple. If you never tried and you just take your time and see how complicated it is, it seems complicated, but it's not really. Okay, this one. Should I draw it? Because it's same principle, right? You draw the free body diagram of point H, pulley H, you have P and P, right? And then reaction at A. And then if you draw the pulley at E, the bigger, smaller, slightly bigger pulley there, you have P, P and P upwards, right? If you draw the point G, pulley G, you have P and P downwards and reaction B, right? If you draw pulley FF, you have the force there, the same force as force downward for E, right? And then if you draw the pulley downwards there, all the upward force is the same force again, right? So it's straightforward, right? So I assume you know what to do, right? So because I'm rushing, I don't have that much time now. Alright, so here, this is quite interesting because we have not seen some of this support type for quite some time, in particular at E, right, I think. So, is there two force member here? There's no two force member, so we'll have basically two member. One is AB, one is BC, right? So, member AB is like this, member BC is like this, basically, right? And then you have force here and force here, right? So straightforward. At point C is CX and CY, right? At point B, of course, you have BX, BY, and then BX, BY. At point A, what do you have at point A? So you should have, one is the normal, one is the moment, right? Hopefully you still remember our discussion in what chapter is it? About support reaction, right? So in this case at A, it can move along the rod there, So the normal reaction is where it cannot move, but also it cannot rotate because it's not pinned but it's fixed, right? So it cannot rotate. So you have force normal there. In this way, it's free to move, right? This one is not free to move, and then it cannot rotate also. Right? Next. Okay, pause, take your time to draw the free body diagram, and then continue again. So basically, first question, is there any two force member? Yes, it is. There is basically BD, right? So BD. If we assume it's under tension, so the way we draw this member here, and then you have another pulley here, right? If I draw the pulley here, right? So at A you have normally AX, AY, of course, and then at B here, if this is assumed tension, this will be like that. And then we have from the cable here, same here as the cable, and this force, it should be the same here. Let's say this is T, 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 right? And then you have 12 kilonewton there, right? And that's it, right? So how to solve is, you solve here, you get T. From this T here, you have 1, 2, 3 unknown, you can solve this one, right? So again, as you can see, if you understand the free body diagram, normally it's not that difficult. And once you get the free body diagram, the rest is just calculation, right? Okay, nice. Pause, try to draw the free body diagram, and then we'll continue. Alright, so this is quite interesting. First, you have to be able to imagine what's going on, right? And basically, you are pressing at the end there with P, and then as a result, it is compressing the wooden block at E, right? So, right. So if we start from the block there, the block here, right? This block here is being compressed. Hence, if you have the whatever this thing here, right? This whole thing, something like this, right? Then you have the force. Okay, I'll draw the force in different colors. So obviously you have force F here, right? This is all F because the question will give you F there. So here, and then the rest is just at point D and C is pin support, right? And I'll draw this top here first, so you have something like that, and then it's basically have something like that, right? So basically you have force F here, and then at D you have, for example, dx dy, for example here dx dy, right? So it's just equal and opposite, right? Now for this point here, okay, we'll draw the two connecting points there first. So let's say something like this, and something like that, right? And at point C, if you assume this is Cx, Cy, so this one will be Cx, Cy, right? Equal and opposite. And then at point this is A, if this is Ax, Ay, so it's Ax, Ay, like that, right? Ax, Ay, Ax, Ay. And then there's point B here. So if it is Bx, By, so you have Bx, By. And of course, here you have P and V. Right? So basically, that's basically the free body diagram. And of course, how to solve, you start where you have the value and then you move one by one, right? So try also to calculate this one, because here I'm just focusing on the free body diagram. I don't even have the value or the question. I have just the diagram, and I try to illustrate how to draw the free body diagram, right? So you can find in the textbook what is exactly the question, and you can try, right? And it should be straightforward here if you already have the free body diagram, right? So next, this one, let's look at that, pause and try to draw the free body diagram and then continue. Okay, the first question is there two force member? Yes, there is, which is CD, right? So member, so if I draw the like that, and then we have that, and then two force member, right? Okay, so if you assume two force member is under compression, so meaning this one will be like that, FCD. At the end here you have F, and then point B here, if this is BX, BY, so it's BX, BY, and then at here you have AX, AY, and then you have here normal force E. Right. So again and again and again, I think if you have enough practices with free body diagram, it will no longer seem scary or intimidating. Right. Try this. Okay. Okay. So the first question: is there any two force member? There is, which is member DE. Right, member DE. So if you have this whole thing here, is this too big? Alright, so those are the members, right? So basically, if you start from the two force member, if this is under compression, so correspondingly this one is corresponding to this one, right? Here somewhere there, here is corresponding to this one there, right? And if I start here, this is point D, right? This where this is F D E, for example, F D E, F D E, F D E, right? Now, and then point C. So if C here is corresponding to C here, right? So if you have CX, CY, so you'll have CX, CY. Right, what else? And at point B here, with this B, right? So you have BX, BY, then you'll have BX, BY there. What else? Of course, this one you have 20 and 20 here. You see? And then the last one is, okay, if you actually draw also the thing being cut in the middle there at A, so this one will be compressed like that, so you'll have FA here, something like that, FA there. Right, so that's how you draw the free body diagram. Now, actually in the class we did try to solve this question. If you want to go through all the question like this in the class that we actually have recorded, also go to the playlist where we record the class session, right? Not the lecture lesson for the flipped classroom like this, the class session where it's actually in the class where the students are there, right? So we have done some of the question like this. Obviously the camera will be much further than the whiteboard, like compared to this one, but we did cover some questions there if you are interested, so go check out for that playlist, right? We'll go straight. What about this one? Again, is there any two force member? There is, right? So member BE is two force member, right? So basically, let's say if you have the wood there, and then you have, oops, there. Okay, my drawing is too big already. Right, something like that. So, member BE, let's consider is under compression. So corresponding to this one is here, right? So you have BE. Of course, you have forcing here. Is it in the frame? Yep. And then at point C here, corresponding to this one, right? So if you assume, let's say, CX, CY like that, so it will be CX, CY like that, for example, right? And then D here you have DX, DY, for example. Of course, this one is being clamped, so obviously this one will be FA like that, right? So that's basically the free body diagram, and that's the end of the examples. So as we can see, if you have enough practices, all the free body diagram is not difficult at all. Of course, that's one step, that's the first step. After that, you have to solve, for example here, how to solve all the question from all the values, for example. So that is another skill that you have to try, right? So in this lecture, we are focusing on the concept. Hopefully you know how to get from the original diagram to the free body diagram, how to understand everything there, get the free body diagram, and just after that it's just equation of equilibrium, right? So please do try, and if there is any question, etc., please do ask. We'll end the session here, I think, inshallah. Next will be the next topic, because this is the end of chapter 6. Alhamdulillah. So we end here. Subhanakallahumma bihamdik, ashhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Assalamualaikum warahmatullahi wabarakatuh.